if y, the received vector y from 1 to n, and x at w are jointly typical, if y from 1 to n and x at w hat are jointly typical, and there is no other k not equal to w hat, such that y1 to n and x k are jointly typical, then the decoder returns w hat. So if this is true, if there's a message so that there's exactly one code word that's jointly typical with what you observe, then the decoder will report that code word. Otherwise, w hat is 0. In other words, a decoding failure occurs.
Excuse me. I don't know the other method, but is it checking any cross correlation between
the maximum likelihood method does this. If we have, it says w hat is equal to argmax over all w of the probability of the observation given this. So in other words, you look over all the w's and pick the one that maximizes this probability. So this is different, but we're going to show that it doesn't matter. I mean, that's the optimal, so anything else is suboptimal, in other words, doesn't do as well. But it will turn out that the cases where maximum likelihood does well and this doesn't are negligible in probability. So, in other words, decoding failure happens if either there is no message that's jointly typical with the observation, or there is more than one message that's jointly typical with the observation. So you can think of joint typicality, the observation, there will be sort of a sphere of code words around that observation that are jointly typical with it. And if there's exactly one message that is in that sphere, then we'll pick that, we'll pick that message. And finally, an error occurs if what we guessed is not equal to what we sent. And we will let this script E be that event. In other words, the event that an error occurs. Okay, so analysis. What we're going to do is we're going to calculate average error probability over all code words and all code books. let's say prop P of script E is that average error probability. So then what we're going to do is, remember the notation, this will be equal to the sum of overall possible code books of the probability of that code book occurring times the average probability of that code book. So remember this notation, that's the average probability of a particular code book. The average probability of a code book is the sum over all messages of the probability of that message times the probability of error given that message, and we gave a particular name to. That was lambda sub W. That's the probability of error for message W. I'm going to add bracket C here to emphasize the dependence on the particular code book C. The probability of the message, that's uniform at random over all of the possible messages, so what is that? How many messages are there?
2 to the n.
2 to the n, so 1 over that, right? 2 to the minus nr.
Excuse me.
Yes?
Could you explain this formula you have there?
Right here?
Yes, that's the error probability of all messages in a code book?
Yes, so this is the average error probability over a given code book. So if I specify the code book, then this is the average error probability of that code book.
And you're multiplying the probability of the message
Yes.
with?
This is the probability of error given that a message W was sent.
W omega, lambda WC.
Yeah, this is the same. And this is the notation we introduced a couple of classes ago. So in other words, this probability of error is the sum over all code books, probability of the code book, sum from W1 to 2pnr of 2 to the minus nr lambda W of C. Let's rearrange that a little bit. 2 to the nr is not dependent on any sum, so I can take that right out. And what I'm going to do is I'm going to change the order of summation. I'm going to do this last. Okay, let's look at this inner sum. What is this? This is, in fact, let's write that separately. In words, this is the average error probability of message W